Hello there, and welcome. Tonight, we're taking a slow dive into the strangest neighborhood will ever belong to our solar system. Not the one from textbooks, not the tidy lineup of planets, but the one with boiling moons, backwards orbits, ghostly storms, diamond rains, and a planet that spins sideways like it's shy. This isn't a system that just sits there in space. It pulses. It warps. It breathes. And tonight, you'll hear 100 facts about it that are so strange, so beautifully wrong-feeling, they'll change how you see the sky forever. If you thought you knew your cosmic backyard, think again. And while you're settling in, before your eyes grow too heavy, I'd love it if you gently tapped subscribe or pressed the little hype button YouTube recently added. It's a small click, but it helps keep these experiments and explorations orbiting out into the algorithm. You can also leave a comment telling me where you're listening from and what time it is in your corner of the night. It's oddly fascinating to see where people are drifting off with us, scattered across the world like stars across the galaxy. Now take a deep breath, let your day drift away, and let's travel together into the quiet corners of the universe. The sun rises every morning, and we greet it without thinking. A familiar warmth, a distant star that feels more like a background presence than a force of nature. But that comfort is a kind illusion. The sun is not gentle, it is not tame, and it is not yellow. Up close, if you could stand the searing radiation and the soundless violence, you would see something closer to white fire, a furious brightness that washes out all color. The sunlight we see filtered through Earth's atmosphere scatters shorter wavelengths, leaving behind that golden glow. But in space, the sun blazes with a full spectrum. It is not yellow. It is every color at once, and it's always changing, not like a flickering candle, but in great cycles of upheaval. Every 11 years or so, the sun's magnetic field flips. The north becomes south, and the south becomes north, a complete inversion of its invisible scaffolding. It's not just a curiosity, this shift brings turmoil. Sunspots multiply, solar storms rise, loops of magnetic energy twist and snap, releasing flares of radiation that ripple through the solar system. These aren't fireworks. They're eruptions of charged particles, lashing out across millions of kilometers, sometimes striking Earth's magnetic field and painting the poles in glowing curtains of aurora. One strong enough, and it could cripple satellites, disrupt communications, even knock out power grids. The sun is not peaceful. It is a restless engine. It throws tantrums the size of planets. Solar flares can grow larger than Earth, born from tangled magnetic lines that suddenly break and reconnect in a burst of raw energy. In minutes, they release more power than all bombs humanity has ever made, combined. Sometimes these flares are followed by coronal mass ejections, great bubbles of plasma flung into space, sailing silently through the vacuum. If they hit us, they don't burn skin. They rattle the atmosphere, confuse instruments, and leave behind electronic echoes. They're storms without sound, impact without flame. And still, the sun is always losing itself. Every second, it sheds around 4 million tons of mass. Not in chunks, not in any visible way, but in the conversion of matter into energy. Through the quiet fury of nuclear fusion, hydrogen atoms are pressed together in its core, becoming helium and releasing light. That light is what warms your skin. That light is why Earth exists at all. But behind it is lost mass transformed, cast outward as radiation. Over the lifetime of the sun, it has given away an unfathomable amount of itself. It is a bright surrender, a stellar sacrifice that keeps us alive. Yet there is something almost eerie in the precision of it. The sun pulses, not with light, but with rhythm. It sings, not in sound as we hear it, but in waves, slow, deep oscillations that ripple through its interior. Astronomers call it heliosismology, Like a bell struck from within, the sun vibrates in patterns that tell us about its internal structure, its layers of plasma and fusion. These starquakes are measured with instruments so sensitive they can detect motion smaller than a human hair. We cannot hear it directly, but if we could translate it, the sun would be humming in deep, sonorous tones, a constant chorus from 1,000,000 kilometers away. We think of the sun as eternal, a permanent fixture in the sky, but it's changing every moment, not just in cycles or flares, but in the slow evolution of its core. As hydrogen is consumed, the balance of forces within shifts. One day, long from now, it will swell into a red giant, swallowing Mercury, then Venus, and perhaps even Earth. But that's another story. For now, in this era, it is steady only in appearance. There is something humbling about knowing the thing that feeds us is also shedding its own mass to do it, that the sunlight hitting a leaf, warming a rooftop, or glinting off the ocean is energy released by atoms fusing in a chaos we can barely imagine. That somewhere in that blaze, a flare larger than the planet might be blooming right now, unseen. We live beside a star, a white-hot, churning sphere of hydrogen that hums and burns and breaks itself apart to keep us lit. It does not burn like fire, it fuses. It does not glow gently, it roars. But from 150 million kilometers away, we are sheltered by distance. We can forget what it truly is until the facts remind us. The sun flips its poles. It sings. It blasts waves of energy into the void. It shrinks as it shines. It loses 4 million tons a second, and still it burns. We orbit not a lamp, but a living force. A star among billions, stranger than fire, and far more powerful than it ever appears from Earth. Mercury is the closest planet to the sun, and yet it is not the hottest. That title belongs to Venus. It's one of many things about Mercury that feel backward, out of sync, or quietly wrong. We picture the inner planets as a neat lineup, where distance means temperature, size suggests gravity, and rotation follows a simple rhythm. But Mercury exists like a misprint, a planet that doesn't quite follow the rules, whose behavior makes sense only when you look closer, when you abandon assumption and let the facts undo your instincts. The temperature extremes are sharp. On the side facing the sun, Mercury's surface can reach over 430 degrees Celsius, hot enough to melt lead. But without a thick atmosphere to trap that heat, the night side plunges to -180. There is no blanket of air to soften the transition, only a silent rotation under the sun's glare, and then away from it. You might expect this rapid change to come with rapid motion. But Mercury's day, the time it takes to rotate once, is longer than its year. It completes an entire orbit around the sun before it finishes a single spin. You could watch the sun rise, crawl halfway across the sky, and then drift backward before finally setting. Days later, time on Mercury is elastic, measured in strange loops. Its surface is battered and silent, painted with scars from a history of impacts. But even now, the planet is shrinking. As its iron core cools, it contracts, and when it does, the crust above it crumples and folds, creating vast cliffs and scarps that stretch for hundreds of kilometers. These aren't the marks of erosion or tectonics like on Earth, they're wrinkles. Deep planetary wrinkles formed as Mercury tightens inward. It is, in the most literal way, growing smaller. Scientists estimate it has shrunk by as much as 7 kilometers in radius over billions of years. You can see the stress frozen into its crust, the pressure of an old body trying to contain its fading heat. And yet, for all this harshness, the baking light, the bitter cold, the shrinking sphere, something cold and persistent has survived. At Mercury's poles, where the sun never fully reaches, lie craters in permanent shadow. Within these shadows, temperatures stay low enough to preserve something you wouldn't expect so close to the sun. Water, ice. Actual frozen water, nestled in the darkness of polar craters, untouched by the planet's brutal days. It likely arrived by comet or asteroid impact long ago, and somehow, impossibly, it remains, not as vapor or trace molecules, but as solid ice, sheltered by geometry and coldness from the very star that rules Mercury's sky. The surprises continue. Mercury is tiny, only slightly larger than the Moon, and yet it has a magnetic field. That alone is strange. Earth's field is generated by a spinning molten outer core, but Mercury's small size should have cooled its core into stillness long ago, and yet, somehow, it persists. A weak but detectable field, tilted and offset from the planet's center, loops around it like a lopsided shield. Scientists believe part of Mercury's core is still liquid, convecting just enough to maintain that magnetic presence. It's a reminder that beneath the silent surface, something is still stirring, a slow heartbeat beneath the rock, and that heartbeat resists easy explanation. Mercury breaks patterns. It doesn't shine with volcanic activity like Io, or hold an atmosphere like Earth, or reflect the cloud-wrapped beauty of Venus. It's quieter, stranger, a planet that rotates too slowly, heats unevenly, shrinks quietly, and holds frozen water in one of the hottest places in the solar system. It is not dramatic, not photogenic, but it is endlessly wrong in ways that only deepen its mystery. To see Mercury is to peer through the sun's glare at something ancient. It formed quickly in the early solar system, its heavy metals sinking to the center while the lighter materials burned or blew away. It is the densest planet after Earth, and more iron than rock, a relic of formation, stripped to its core, still clinging to motion and magnetism after 4 billion years. No spacecraft has landed there. Few will ever visit. But from afar, with radar and probes, we watch, and the closer we look, the less it resembles what we thought a planet should be. Mercury exists in defiance of category, too small to be dynamic, too close to the sun to hold ice, too slow to keep time, too quiet to draw attention. But in all of these things, it becomes something else, a planetary contradiction, a reminder that in the solar system, distance does not always equal heat. Mass does not always mean motion, and the smallest bodies can still hold secrets more profound than size or shine would suggest. It is not the hottest, though it is closest. It shrinks as it cools, leaving scars that stretch like stories across its Themaria and face. Its days are longer than its years, and its poles are colder than you'd expect. Ice hides in its shadows, and against all odds, it carries a magnetic field, an echo of liquid motion buried within metal and time. Nothing about Mercury is obvious. Nothing about it is easy. But maybe that's why it matters. Because in its wrongness, it shows us something important. That the universe isn't built for our expectations. It doesn't care about symmetry or narrative. It creates what it will. And sometimes, what it creates is a small, hot, slow-spinning world that holds ice, shrinks quietly, and hums with a magnetic field beneath the silence. A planet that challenges every assumption we bring to the sky and leaves us better for it. Venus looks beautiful from afar, wrapped in thick, golden clouds. It shines brightly in our sky, second only to the Moon in nighttime brilliance. Early astronomers called it Earth's sister, even Earth's twin, similar in size, similar in mass. A planet that might once have seemed like another home. But that illusion dissolves quickly under closer inspection, because beneath those clouds is a place of such unrelenting violence and heat that it becomes difficult to believe it exists in the same system as us. Venus is not a twin. It is a mirror warped by catastrophe. Its rotation defies expectation. Venus spins backwards, slowly, almost lazily, in the opposite direction of most other planets. If you stood on the surface somehow protected from the crushing pressure and furnace-like heat, you would watch the sun rise in the west, and set in the east, but not quickly. A single day on Venus, from sunrise to sunrise, takes the equivalent of 117 Earth days. Stranger still, its year, the time it takes to orbit the Sun, is only 225 Earth days. This means that a day on Venus is longer than its year. You could live through an entire orbit before seeing the Sun complete its slow, ghostly arc across the sky. And that sky would not be kind. The atmosphere of Venus is a thick, choking soup of carbon dioxide, with clouds of sulfuric acid drifting high above. These clouds reflect sunlight, hiding the surface from view and trapping heat beneath them in a greenhouse effect so extreme that the entire planet has become an oven. The surface pressure is over 90 times that of Earth's, the equivalent of being nearly a kilometer underwater. And the temperature? Over 460 degrees Celsius, hot enough to melt lead, hot enough to destroy spacecraft in mere hours. The Venera landers from the Soviet Union managed to survive the descent and send back images, but none lasted more than 2 hours before they failed. Venus eats machines. It also rains acid. Not in the way we know rain. The sulfuric droplets in the upper atmosphere evaporate long before reaching the ground. But the clouds are still thick with corrosion, and the sky is filled with the chemistry of decay. There is no water on Venus, none in its air, none on its surface. Whatever it once had has long since boiled away, lost to space, or locked in the minerals of its crust. And yet, Venus may not be dead. Beneath its searing heat and thick atmosphere, there are signs that its mountains may still be volcanic. Surface features captured by radar suggest flows of lava that look geologically young, and temperature readings from orbit hint at hotspots, regions that flicker and change, as though something below is still breathing heat. If true, Venus may still erupt. Its volcanoes may still stir in the shadows, hidden by clouds, reshaping a surface we can barely see. It's difficult to accept that this is the same kind of planet as Earth. They are nearly identical in diameter. Their compositions are similar. They may have formed from the same primordial ingredients, and yet one is blue, filled with life and liquid oceans, while the other is a suffocating inferno, hostile to even the most basic molecules of biology. What separated their fates? Some scientists believe Venus may have once had oceans, that it began more temperate, more hospitable. But its proximity to the sun allowed runaway heating to begin. Water vapor, a potent greenhouse gas, rose into the atmosphere, trapping more heat, evaporating more water, until the oceans were lost. The hydrogen drifted into space, the carbon stayed behind, and the planet turned itself inside out. It is a reminder that similarity does not mean safety, that two things can begin almost the same and end in opposite states. Venus is what happens when a planet spirals out of balance, when its air becomes poison, when its clouds trap not softness, but fury. It is not simply hot, it is devouring, not simply bright, but blinding. A world of reverse time, corrosive rain, and mountains that may still smolder under acid winds. And yet, it is compelling. To study Venus is to study the limits of survival. To wonder if we could ever walk there, live there, shielded inside. Floating cities in its upper atmosphere, where temperatures and pressures are more forgiving. Some scientists imagine such missions. Others look to Venus to understand climate itself, a case study in what happens when feedback loops go too far. It is not just a planet, it is a warning. Above the clouds, it still looks beautiful, smooth, inviting, a soft golden glow in the evening sky. But beneath that glow is a place where time is twisted, where the air itself is a weapon, where the ground bakes in perpetual fire, and the mountains may still grumble in molten silence. Venus is Earth's twin, only in body. In spirit, it is something else entirely. A reminder that likeness is not destiny, and that beauty from afar can hide a world of unrelenting heat, silence, and ruin. Earth feels stable, solid, familiar. We walk across it with confidence, drink its water, trace the arc of the seasons like clockwork. It is home, and for most of human history, it has seemed like the center of everything. Even now, with all we know, we speak of it as special, the only known planet with life, with oceans, with consciousness looking back at the sky. And yet, much of what we take for granted is not fixed. Earth's balance is fragile. Its story is ancient and full of motion, quiet shifts, deep reversals, and strange inheritances. The ground beneath our feet is still drifting. The compass we trust has not always pointed north. Even the water we hold in our hands may be older than the sun itself. Start with the tilt. Earth leans at about 23.5 degrees, a slight angle that gives us seasons, variations in sunlight, and the rhythm of growing and resting. But that angle isn't constant. Over thousands of years, it wobbles like a spinning top. This slow oscillation, called axial precession, shifts the orientation of Earth's axis in a circular pattern, completing a cycle roughly every 26,000 years. The result is subtle, but powerful. It alters the position of stars in the sky, over millennia, nudges the timing of solstices and equinoxes, and helps drive long-term climate patterns. What feels fixed, the arc of the sun, the depth of winter is slowly evolving, too gradual for a human lifetime, but relentless all the same. And this tilt, this slow dance, would be far less stable without the moon. Earth's large satellite does more than light the night sky or pull the tides. It acts as a stabilizer, a gravitational anchor that damps the chaotic wobble that might otherwise plague a planet of our size. Without the moon, Earth's axial tilt could vary wildly over time, swinging between near zero and extreme angles that would distort climate and seasons beyond recognition. The moon holds our balance, quietly, invisibly. It makes our world livable not by light, but by gravity. It steadies our spin, tugs gently at our oceans, and reminds us that even our rhythms are shared. But some things go back much further. The water in our oceans, rivers, and even our cells may not have formed here at all. Some of it likely predates the sun itself. Before the solar system was born, before the planets coalesced, there were ancient clouds of gas and dust swirling in space. Within those clouds, water molecules formed on tiny grains of dust, frozen in the coldness between stars. When the solar system took shape, some of that primordial ice was captured by comets, asteroids, and the building blocks of planets. That water, older than Earth, older than the sun, eventually rained down onto our planet billions of years ago, and stayed. When you drink a glass of water, you may be holding something forged in the darkness before the sun ever shone, a memory of interstellar cold, trapped in a droplet. Even the deep core of our planet is not still. Beneath the crust, beneath the mantle, lies the outer core, a churning sea of molten metal, mostly iron and nickel. This movement generates Earth's magnetic field, a shield that protects us from solar wind and cosmic radiation. But that field is not permanent and not always stable. It has reversed many times in the past. North becomes south, south becomes north. The process is not instant. It unfolds over thousands of years, during which the field weakens, fractures, and reorients itself. These magnetic reversals are recorded in rocks, frozen into the patterns of ancient lava flows. They are part of Earth's history, but not part of everyday experience. If you lived through one, you might not even notice except for the slow drift of compasses, the quiet reshaping of our invisible barrier against space. And still, beneath all of this, the continents move, not with earthquakes or eruptions, but with the slow patience of geology. The tectonic plates that make up Earth's crust glide over the mantle like rafts on a viscous sea. A few centimeters a year, maybe less, but over millions of years, those movements rewrite the face of the planet. They birth mountains, carve oceans, and bring once distant lands together. The Himalayas are still rising, the Atlantic is still widening, and someday the continents will gather again in a new supercontinent, a future Pangea, rearranged by forces we can barely feel. The ground you stand on today is not permanent. It is drifting, inch by inch, on a journey far longer than any human memory. Earth is not as still as it seems. Its seasons shift over cycles of tens of thousands of years. Its axis is cradled by the moon. Its water holds the fingerprints of a time before the solar system. Its magnetic field can reverse, and its surface drifts like a slow tide of stone. We live in a moment, and the planet plays out its patterns over eons. It may be the only world we know with life, but it is not untouched by the universe around it. Its balance is not a guarantee. Its features are not fixed. Earth is a story still being written, not a fortress, but a dance of ancient forces that have shaped it for billions of years and will continue long after us. It is special, but not because it is perfect, because it is fragile, because it is still becoming. The moon feels like a relic, as if it were finished long ago. A fossil hung in the sky, unchanged and silent. We imagine it as ancient stone, locked in stillness, circling Earth in the same slow arc it's followed for billions of years. But the moon is not as settled as it appears. It may be old, but it is not done. Beneath the stillness, things are still shifting. The moon is still evolving. Each year, it drifts a little farther from Earth. Not quickly, not dramatically, about 3.8 centimeters annually, roughly the rate at which fingernails grow. It happens because of tides. Earth's oceans, pulled and pushed by lunar gravity, tug back in return. Over time, this exchange of energy transfers momentum to the moon, nudging it outward. It was once much closer, looming larger in the sky, dominating tides and stretching Earth's crust. In the distant future, it will drift so far that total solar eclipses will no longer be possible. That perfect moment, when the moon precisely covers the sun, will become a thing of the past. All because of this quiet recession, the slow unraveling of an ancient gravitational partnership. And while it moves outward, the moon is not entirely quiet inside. Moonquakes are real. Some are shallow, caused by meteor impacts or thermal expansion from sunlight. Others are deeper, more mysterious, coming from within. These aren't like earthquakes. There are no shifting plates or active volcanoes. But the moon is still under stress. As it continues to cool, its interior contracts. The crust above buckles and cracks, releasing energy. Some of these quakes last far longer than those on Earth, rumbling for 10, 20, even 30 minutes. There is no water to absorb the shock, no atmosphere to dampen the waves. The vibrations ring through stone like sound through a bell. And that's not just poetic metaphor. The moon really does ring. During Apollo missions, seismometers were left on the surface. When spent rocket stages were deliberately crashed onto the moon to test those instruments, the resulting vibrations echoed far longer than expected. It rang like a bell, softly but clearly, as if the entire body of the moon was resonating. Not because it's hollow, as some have speculated, but because of how its dry, rigid crust carries seismic waves, a bell made of silence, ringing in vacuum. But even in that cold silence, there is water. In the deep shadows of craters near the lunar poles, places where sunlight has never reached, frozen water has been detected. These shadowed basins act as cosmic freezers, preserving ice for eons. No atmosphere, no warmth, no chance for melting. Just the darkness and the cold, holding onto molecules of water that likely arrived via comets or solar wind reactions. This ice is ancient and untouched. It might someday be the key to surviving on the moon, a resource for drinking, fuel, or air. But for now, it sits quietly, a hidden memory beneath the dust. And perhaps that dust carries a deeper connection than we once believed. For a long time, the moon's origin was unclear. Too big for a captured object, too different in composition to have formed beside Earth. But the leading theory now tells a stranger story. That long ago, a Mars-sized body collided with Earth in a cataclysmic impact. The force of it vaporized crust, melted rock, and hurled debris into orbit. From that ring of fire and fragments, the moon slowly coalesced. We may be made of the same event, Earth and moon, born from the same violent beginning. If that's true, and all evidence continues to support it, then the moon is more than a companion. It is kin, formed from our shattered body, orbiting still, holding the scars of our shared trauma in every crater and ridge. That impact changed Earth forever. It tilted our axis, gave us our seasons, and may have created conditions ripe for life. And from its ashes came the moon, which in turn stabilized Earth's tilt and slowed its rotation. Without that impact, life as we know it might never have been possible. It wasn't just destruction, it was transformation. Today, we look up and see a face of stone, a place where no wind blows, where no river runs, where shadows are sharp and unbroken. But beneath that stillness, the moon continues to change. It moves away, it quakes, it holds water in the darkness, and it echoes with its own slow music. It is not static. It is not done. It is a partner still evolving, still responding to the forces that shaped it. We often treat the moon as a finished story, a punctuation mark in the sky, but it is more like a page still turning, a remnant of fire, a keeper of ice, a quiet witness to Earth's entire history. And as we return to it, with new missions and new eyes, we may find it has more to teach us about impact, about motion, about memory carved in stone. Because the moon is not just watching us, it's still becoming. Mars is dry and quiet now, a planet where silence clings to the soil and time feels frozen. But that stillness is deceptive. Mars is not entirely dead, not entirely at rest. It moves in ways that are subtle, in cycles of dust and wind, of ice and thaw. It is a world that sleeps with one eye open, shaped by an ancient past and perhaps holding on to the last breaths of its once lively atmosphere. At its poles, Mars still breathes, not with lungs or seasons like Earth's, but with the slow rhythm of its ice caps. These frozen sheets, made of water and carbon dioxide, expand and retreat as the planet tilts and shifts through its seasons. During winter, the polar caps grow, fed by gases pulled from the thin atmosphere and turned to frost. In the summer, under sunlight that barely warms, they shrink back, releasing gases that swirl into the sky. This isn't just surface change, it's climate in motion, a Martian breath exhaled in dust and vapor. And in that dust, the planet comes alive. Thin as its atmosphere is, Mars still conjures wind. Small whirlwinds called dust devils twist across the surface, painting dark trails as they snake over plains and hills. Some are small, barely visible from orbit. Others tower kilometers high, swirling silently in the low-pressure air. But sometimes, these localized dances give way to something larger. Global storms can rise from seemingly nothing, shrouding the entire planet in a sepia-colored haze. Light disappears. Solar-powered landers go blind. The temperature drops. The last great storm in 2018 engulfed everything, and one of our longest-running robotic scouts, Opportunity, went silent beneath the dust and never woke up. Still, Mars remains a place of hints, a planet of almosts and maybes. For decades we searched for water, and now we know it's there, locked in polar ice, hiding in frost, and possibly flowing beneath the surface. In 2018, radar data from the Mars Express orbiter revealed something extraordinary. A possible lake, deep beneath the south polar ice cap, trapped under pressure and brine. Not a rushing river or open sea, but a pocket of liquid in the cold. A dark reservoir, untouched, unseen, and perhaps ancient. If it exists, and new findings continue to support it, it could be a haven for microbial life. A place where warmth and chemistry might still stir something small, something patient, something surviving. Look up from the surface, and Mars offers another surprise. Its sunsets are the reverse of ours. During the day, its sky is butterscotch and pale red, colored by iron dust suspended in the atmosphere. But when the sun dips low, something strange happens. Scattered light, filtered through that same dust, turns the sky near the setting sun, a soft, ghostly blue. Not the deep blues of Earth, but a cooler hue that lingers just above the horizon. It's a moment of inversion, as though the planet holds a memory of Earth's skies in the quiet of its own. Mars, for all its desolation, wears the marks of a once different self. Rivers once carved its surface. Valleys and canyons, now dry, hint at flows that lasted thousands, perhaps millions of years. Minerals that only form in water have been found across its terrain. Ancient lake beds, delta fans. The fingerprints of water are everywhere, as though the planet has been trying to tell us for centuries. I was not always like this. Long ago, it may have even had a magnetic field, the kind that could shield an atmosphere, push back solar wind, and protect a more temperate climate. But that field vanished. No one knows exactly why. Maybe the core cooled too quickly. Maybe convection stopped. Maybe some deeper instability flickered out. Without it, the planet's atmosphere was peeled away by the sun over time. What remains is thin, tenuous, more whisper than wind, and can no longer support rivers or protect surface lakes. But traces of magnetism remain, locked in ancient rock, like the echo of a heartbeat that once was. And yet, the story of Mars isn't over. It may be colder now, quieter, with an atmosphere so fragile that water boils away at the surface even when it should freeze. But below the crust, there are still questions, still warmth, still chemistry. Mars is a relic of what a world can become when the balance is lost. But perhaps it is also a bridge between lifelessness and life, between Earth's abundance and the emptiness that waits beyond. It's easy to think of Mars as finished. A red marble, blown dry by time. But then you watch the dust lift, or see the polar cap shift, or catch the blue of its sunset, and you're reminded that this planet is not gone. It's just waiting. It changes slowly, whispers in wind and shadow, and keeps its secrets tucked beneath layers of frost and stone. It may not be dead, just quiet, and still holding on. Between Mars and Jupiter, there lies a silence made of stone, a band of scattered rock and ancient debris drifting in orbits that never quite coalesced into a world. The asteroid belt is not the chaos it's sometimes imagined to be, not a wild field of tumbling boulders crashing into one another, but a quiet, mostly empty expanse where pieces of a possible planet linger, circling endlessly through space. It is not a graveyard. It's a cradle that never held what it was meant to. We once thought a planet had shattered there, that some ancient world had been torn apart, leaving behind only fragments. But that story doesn't hold. The truth is quieter and stranger. The total mass of the asteroid belt is less than 1/20th of our moon. Even if every rock and dust grain were pressed together, it wouldn't make a planet not even close. Instead, it's more likely that a planet never formed at all. That in the early solar system, when gas and dust clumped into worlds, something prevented this region from finishing the process. That something was Jupiter. Its gravity, immense and relentless, stirred the material like a spoon in a bowl, preventing it from settling. Where order tried to emerge, Jupiter pulled it apart. It didn't destroy a planet, it stopped one from ever existing. The result is a region filled with gaps, clearings in the belt, where the pull of Jupiter's orbit disrupts the motion of any object that dares to linger. These are called Kirkwood gaps, places carved out not by collision, but by rhythm. Every time an asteroid tries to find a steady path within those resonant zones, it's nudged off course, not violently, just enough. Over centuries and millennia, the space clears. Gravity sculpts emptiness, but what remains is far from uniform. Some asteroids are little more than rubble, held together by their own weak gravity. Others are worlds in miniature. Vesta, one of the largest, carries hints of volcanoes, evidence that, for a time, it may have been geologically active. Unlike most of its companions, Vesta shows signs of internal heat, past differentiation, and even lava flows. It almost became something more. Almost. But like everything else in the belt, it was stopped just short of transformation. Some of these fragments have moons of their own tiny rocks, orbiting slightly larger ones. Ida, a lumpy, cratered asteroid, has a companion called Dactyl, just a kilometer across. These systems are delicate, held together by gravity so faint it's almost imagined. But they persist, spinning through space together, reminders that even in smallness, there can be structure, there can be orbit, there can be relationship. The scale of these bodies is hard to grasp. Many of them are small enough that you could walk across them, step by careful step, but you'd have to move slowly. The gravity is so weak that a brisk jog might launch you into space. On some, you could leap and never return. It's not just about being light, it's about the absence of downward pull, the nearness of escape. Standing on an asteroid would feel like balancing on the edge of falling forever. And yet, these places are real. They drift between the familiar warmth of Mars and the distant churn of Jupiter, holding records of the solar system's earliest moments. Their surfaces are ancient, unweathered by wind or water, marked only by collisions and sunlight. Every crater tells a story of something that passed too close, of motion interrupted. They are, in many ways, the memory of a beginning that didn't finish. The asteroid belt is not loud, it is not dramatic, but it is deeply honest. It doesn't pretend to be something it's not. It holds its failure openly. It could have been a planet but wasn't, could have gathered into something round, warm, and layered, but didn't. It stayed scattered, broken, waiting, and still, we find value in it. Not because of what it became, but because of what it holds. Water-rich asteroids may one day support missions, refuel rockets, or offer resources beyond Earth. Metal-rich ones may hold precious elements formed in the cores of stars. Some scientists think the building blocks of life, the organic molecules that seeded Earth, may have come, at least in part, from asteroids like these, delivered by impact, carried across cold space and time. We once feared them, imagined them only as threats. The extinction of the dinosaurs began with an asteroid, after all. But now, we study them, send missions to them, touch their surfaces with robotic arms. In 2020, a spacecraft called OSIRIS-REx reached out to Bennu, a near-Earth asteroid, and gathered a handful of dust. In the coming years, we'll hold that dust in our hands, read it like a page from the beginning of the solar system. And maybe it will tell us something we've forgotten. The asteroid belt isn't a ruin. It's a possibility paused. A symphony whose final note was never played. It is filled with fragments, but not lost ones. Each stone is where it's meant to be, held in place by gravity and time, circling the sun as it has for billions of years. Not a planet, but still a world worth knowing. Jupiter doesn't have a surface in the way we understand it. No ground to walk on, no place to land and stand. It is a world made of atmosphere, a swirling monument of gas and gravity, layered in bands of cream and copper that stretch for tens of thousands of kilometers. Its storms churn in slow motion, some larger than entire planets. Its winds howl at speeds beyond any earthly hurricane, tearing through hydrogen skies that deepen in pressure and heat the farther down you go. It is the largest planet in the solar system by far, and yet it remains a mystery wrapped in clouds, refusing to show us a solid face. At the heart of its fury spins the Great Red Spot. It's not a mountain or a sea or a crater, but a storm, a cyclone so vast that Earth could disappear inside it with room to spare. First seen through telescopes over 350 years ago, it has persisted through generations of science, spacecraft, and stargazers. Its color shifts slowly over time, from deep crimson to a softer salmon hue, but the storm continues. Winds within it whip at over 400 kilometers per hour, swirling counterclockwise in a vortex more ancient than any human city. It's shrinking, yes, but it's still alive, still pulsing, still there. Jupiter doesn't just reflect sunlight, it glows with its own heat. The planet emits more energy than it receives from the sun, radiating warmth left over from its formation. When the solar system was young, Jupiter grew rapidly, pulling in gas and dust, compressing under its own weight. That compression generates heat still today, internal energy escaping into the vacuum, making it not just a giant, but a furnace. Deep beneath the clouds, the pressure increases until hydrogen becomes liquid, and deeper still, it may become metallic and exotic, flowing metal that conducts electricity and fuels one of Jupiter's strangest and most powerful features, its magnetic field. This field is the strongest of any planet in the solar system, about 20 times more powerful than Earth's. It stretches far into space, forming a magnetosphere so large it could engulf the Moon's entire orbit around Earth. Trapped within this field are belts of radiation, intense enough to destroy electronics and damage unshielded spacecraft. It is a field that hums and crackles with energy, disturbed by the winds of the sun and sculpted by Jupiter's rotation. It protects the planet like a force field, but it is also dangerous, turbulent, and wild. Around this massive world orbit over 90 known moons, an entire miniature solar system of their own. Some are small and misshapen, caught in erratic paths. Others are worlds in their own right. Ganymede is larger than Mercury, with a magnetic field of its own and a surface of ice hiding a global ocean beneath. Europa may have a saltwater ocean as well, kept warm by tidal forces, with more water than all of Earth's oceans combined. Io, closest of the major moons, is a volcanic fury, its surface covered in sulfur and fire, erupting constantly as Jupiter's gravity pulls and stretches it like clay. Callisto, ancient and battered, holds memories of impacts that go back billions of years. Together, these moons tell a story of motion, heat, and transformation, all orbiting a planet without a floor. And circling all of this, almost overlooked, are Jupiter's rings. Faint, thin, and shadowed, they are nothing like Saturn's grand display. They were only discovered in 1979 by the Voyager spacecraft, hidden in darkness and dust. Made mostly of small particles, likely from meteor impacts on its inner moons, the rings are subtle, more suggestion than statement. But they are there, a quiet adornment on a world that already overwhelms the senses. Everything about Jupiter is motion. Its atmosphere rotates at different speeds depending on latitude, with equatorial regions racing ahead of the poles. Bands form from this differential rotation cloud belts, moving in opposite directions, creating turbulent borders where storms are born. Lightning has been detected within these clouds, some flashes thousands of times stronger than those on Earth. In the infrared, the planet glows with hot spots, bursts of energy rising from deep within. It spins so quickly, completing a full rotation in under 10 hours, that its shape is distorted, bulging at the equator and flattening at the poles. And yet, for all its size, Jupiter is made almost entirely of hydrogen and helium, the same elements that fuel stars. It's often called a failed star, but that's not quite right. It would have needed dozens of times more mass to ignite fusion and begin burning. Instead, it sits on the edge between planet and star, massive enough to shape the system around it, but not enough to shine. Still, its gravity guides the paths of comets, protects the inner planets from incoming debris, and even helped sculpt the asteroid belt by preventing a planet from forming there. Jupiter is both guardian and gatekeeper, holding influence over bodies far beyond its own orbit. To look at Jupiter is to see a storm that never ends, a magnet pulling moons and particles into endless dance. It is not a place we will ever stand. There is no ground to find, only clouds that deepen into pressure and heat beyond what any probe has survived. But from orbit, from afar, it commands awe. It is ancient and volatile, wrapped in noise and silence, burning with the remnants of its birth. Jupiter is not just a planet. It is an atmosphere in constant upheaval, a field of gravity and motion, a spinning monument to the power of gas, time, and pressure. A world made of storms, still growing, still changing, still teaching us what a planet can be when it refuses to be. Still, Europa is not loud. It drifts silently through the cold shadow of Jupiter, locked in orbit, coated in a shell of pale, scarred ice. To the eye, it appears almost gentle white and quiet, marbled with faint reddish cracks that stretch across its face like the veins of ancient porcelain. But this moon is not fragile. Beneath its smooth exterior, Europa hides something immense, something deep, something alive, not in the way of trees or voices, but in the restless movement of water and heat. It is, quite possibly, the most promising place beyond Earth to search for life. Its surface is the smoothest in the entire solar system, not smooth like polished glass, but smooth in terms of terrain. No towering mountains, no vast canyons, just rolling plains of ice with few craters. That lack of impact scars isn't just coincidence. It suggests something below is active, reshaping the surface, erasing the old. When we look at Europa, we're not just seeing ice, we're seeing the skin of a world that repairs itself, a shell of frozen light, hiding motion underneath, and the signs of that motion are everywhere. Cracks, ridges, and long, looping fractures stretch across the ice in tangled patterns. These are not random. They form as the crust is pulled and tugged by the gravity of Jupiter, a force so strong it can flex Europa's interior like clay. This tidal flexing generates friction, and friction creates heat. It's this heat, not sunlight, that is thought to keep a vast subsurface ocean from freezing solid. Europa is far from the sun, bathed in cold and darkness, but it is warm inside. Not from a glowing core like Earth's, but from the endless squeezing and stretching of Jupiter's grip. That ocean, if it exists as scientists believe, would be immense. Not a thin layer, not a buried lake, but a global sea stretching for thousands of kilometers beneath ice that may be anywhere from a few kilometers to dozens thick. And the volume of that ocean? It could contain twice as much water as all of Earth's oceans combined. Imagine that. An entire planet's worth of water, hidden beneath a frozen crust, kept liquid by nothing more than the rhythmic pressure of gravity. There are hints that this water doesn't always stay locked beneath. Some images from passing spacecraft suggest the presence of cryovolcanoes, ice volcanoes, where liquid water or slush may erupt from below, freezing as it bursts into the vacuum of space. These geysers, if confirmed, offer more than just spectacle. They might allow us to sample Europa's ocean without drilling through the ice. They might contain the chemical fingerprints of whatever stirs beneath. Because the question that looms over Europa is not just whether it has water, it's whether that water has company. Here on Earth, life has proven to be shockingly adaptable. In the deep ocean, far from sunlight, entire ecosystems thrive around hydrothermal vents. These black smokers gush superheated, mineral-rich water. And, in the darkness, bacteria feed not on sunlight, but on the chemical energy in those minerals. Larger organisms, worms, crabs, strange translucent fish gather around them, forming communities that live in complete isolation from the sun. If it can happen here, why not there? Europa's ocean could host similar vents. The same tidal forces that heat its interior might drive volcanic activity on the seafloor, creating warm, mineral-rich environments. And if life ever began there, if, somehow, the right molecules found each other and learned to copy themselves, it might still exist, hidden in the dark, carried on currents, feeding, dividing, enduring. We don't know. That's the honest truth. But the ingredients are there. Liquid water, energy, organic molecules, detected in trace amounts on the surface. A protective shell to keep radiation at bay. Europa is not just interesting, it's tantalizing. A question floating 628 million kilometers away. And, yet, standing on Europa, if one could, the silence would be absolute. The sky would be pitch black, except for the looming form of Jupiter, hanging huge in the sky like a god. The ice beneath your feet might groan and shift, pushed by unseen forces. And under that ice, an ocean would slosh and swirl, unlit, unfathomed, and possibly inhabited. A world beneath a world, listening in the dark. Future missions aim to go there, to orbit, to scan, perhaps even to land. NASA's Europa Clipper is being built to study the moon in detail, mapping its surface, searching for plumes, peering beneath the crust with radar and spectrometers. One day, we may drill through the ice, or dive into the ocean below. But for now, all we have are glimpses and dreams. Europa isn't just a moon. It's a whisper from a deeper cosmos. A reminder that life, if it arises, doesn't need sunlight or continents or even a breathable sky. It only needs shelter, water, energy, time. And Europa has had all three for longer than we've existed. It may be waiting, not to be discovered, but to be heard. In the dark quiet beyond Europa, two enormous moons circle Jupiter like forgotten kings. Ganymede and Callisto, massive, icy, ancient. They do not shimmer with mystery in the same way Europa does. They do not promise dramatic geysers or smooth, alluring surfaces. Instead, they seem heavy with age, wrapped in silence and scars. But to overlook them is to miss something vast. Because Ganymede and Callisto are not dead worlds. They are sleeping ones. And inside them may lie oceans, heat, and even traces of magnetic breath. Ganymede is the largest moon in the entire solar system, bigger even than Mercury. If it orbited the sun on its own, no one would hesitate to call it a planet. But instead, it remains a satellite, bound to Jupiter by gravity, tethered to a place that radiates chaos and power. Yet Ganymede holds its own. Beneath a crust of ice and silicate rock, it hides an interior, layered with complexity. There's iron at its core, flowing slowly, just enough to generate something astonishing, a magnetic field. No other moon in the solar system does this. Ganymede is wrapped in its own magnetism, faint but real, resisting the overwhelming force of Jupiter's field with one of its own. It is not a strong shield, but it's a personal one. A declaration of identity in the shadow of a giant. That field creates auroras, not ones we can easily see from Earth, but ribbons of movement at the poles, caused by charged particles funneling down invisible lines. It's a phenomenon we associate with Earth, with atmosphere and color and dancing lights. But here, too, it flickers faintly, in ultraviolet, unseen by the eye, but not by instruments. Ganymede shines in its own way, whispering to the solar wind that it is not just a rock. Beneath its icy crust, like its sibling Europa, Ganymede likely holds a subsurface ocean, possibly a deep one, up to 100 kilometers, down sandwiched between layers of ice. There may even be several oceans, stacked like watery strata, divided by pressure and frozen barriers. It's a complicated structure, shaped by heat from within and the pull of Jupiter from without. If that ocean exists, It may contain more water than Earth, perhaps more than any other body in the solar system. And within that darkness, there could be motion, salt, minerals, maybe even a quiet form of life, drifting through alien tides. But if Ganymede feels young in its energy, Callisto is its elder sibling. Farthest of the Galilean moons, Callisto doesn't rotate in lockstep with Europa and Ganymede. It doesn't participate in the orbital resonance that keeps the others flexing and heated. It moves more quietly, more independently, and its surface reflects that stillness. Of all the major bodies in the solar system, Callisto's surface may be the oldest. 4 billion years of unchanging silence, cratered by time, left untouched by geology. Each impact scar that pockmarks its surface is a frozen echo of something ancient, colliding with what could not resist. These craters tell stories we can't fully read. Some are shallow, softened by the slow flow of ice. Others are deep and sharp, rimmed with ridges and rays. The largest, called Valhalla, stretches nearly 4,000 kilometers from edge to edge, its rings rippling outward like a stone dropped in cosmic water. These aren't just marks of violence, they're signatures of survival. Callisto took the blows and kept moving. It didn't crack, it didn't erupt, it just endured. And yet, for all its stillness, Callisto may not be as inert as it seems. Beneath the battered shell, there may be an ocean too buried so deep it escapes casual detection. A hidden layer, insulated from the cold above by thick, motionless ice. It would be darker than anything on Earth, sealed from light, warmed only by the faint residual heat of formation and perhaps by radioactive decay in the core. But even here, life could exist. The possibilities are quiet, but they are not gone. One of the most intriguing contrasts between these two moons is how they live under Jupiter's rule. Ganymede, orbiting closer, is constantly exposed to Jupiter's intense radiation belts. Its surface is blasted by charged particles, altering the chemistry of its ice, perhaps changing how we interpret the data we gather. Any potential life near the surface would be extinguished by that relentless bombardment. It is a hostile environment, one that demands shelter in depth. Callisto, on the other hand, orbits farther out beyond the worst of the radiation. Its surface is more preserved, more stable. If we were to land there, it might be the safest place among the Galilean moons. Less heat, yes. Less energy, perhaps. But also less destruction. Some scientists consider it an ideal base for future exploration of the Jovian system. A place to observe from, to build from, to begin. Together, Ganymede and Callisto form a kind of balance. One is dynamic, magnetic, sculpted by hidden motion. The other is ancient, marked by the long patience of time. One is shaped by internal flows and glowing auroras. The other is etched by collisions, layered in the dust of eras. And yet both may harbor oceans. Both may shelter secrets beneath the ice. They are not dead worlds. They are worlds that choose silence. We may never walk on them. Their gravity is low, their surface is harsh, their distance vast. But they are not beyond understanding. With each passing mission, each flyby and scan, we learn more. The Galileo spacecraft brought their surfaces into focus. The JUICE mission, now on its way, will study them in greater detail, mapping fields, scanning for oceans, listening for whispers beneath the crust. We do not yet know what moves within them, but we know this. Ganymede and Callisto are not just moons. They are archives, libraries of impact, of heat, of survival. They hold records of how a system was born and how it changed. And maybe, just maybe, they hold more than memory. Maybe they hold life too. Quiet, unseen, waiting beneath the ice. If there were an ocean vast enough, wide and deep and bottomless, Saturn would float in it. Not skim the surface like a skipping stone, but rest inside, buoyant and slow, drifting like a golden lantern on an endless tide. This isn't poetic exaggeration. Saturn's density is so low that it is, by definition, lighter than water. A planet made of gas and haze, so immense in scale, yet so ethereal in composition, that it seems almost too delicate to be real. And yet it is there, unmistakable in the night sky, adorned in rings that shimmer like myths come to life. Saturn's beauty is undeniable. The rings alone make it the crown jewel of our solar system. From afar, they appear solid, wide golden disks, smooth and symmetrical. But up close, they're revealed to be made of ice and rock, shattered fragments of moons or comets, each piece tumbling in its own orbit. Some are no larger than grains of sand. Others are the size of mountains, all of them held in balance by Saturn's gravity, shepherded by tiny moons that dance along the edges like quiet guardians. The rings stretch over 270,000 kilometers from the planet's center, yet they are often no more than a few dozen meters thick. A vast, fragile halo drawn with a precision that defies chance, and they may not last. Recent research suggests that the rings are temporary, that they're already beginning to fade. Micrometeorite impacts and Saturn's own gravity pull the particles down toward the planet, creating what's called ring rain. It's a gentle, invisible snow of icy debris slowly falling into the gas giant's atmosphere. Within a few 100 million years, a blink in cosmic time, the rings may vanish entirely. When we look at them now, we may be witnessing a fleeting stage in Saturn's long life, like seeing a flower in bloom just before the petals begin to fall. Yet Saturn is far more than its rings. Beneath the hazy layers of ammonia clouds and golden atmosphere, it is a world in constant motion. Like Jupiter, it emits more heat than it receives from the sun. This internal warmth, left over from its formation and added to by mysterious processes, drives its weather systems and stirs its deep layers. One of the most curious phenomena sits at its north pole, a storm in the shape of a hexagon. This six-sided jet stream, vast enough to fit Earth within its borders, has persisted for decades, maybe centuries. No other planet has anything quite like it. The shape is not an illusion. It is a stable, rotating structure in the clouds, formed by differences in wind speed and pressure. It spins like a lid, calmly, violent, geometric in a way that nature rarely is, deeper still, beyond what we can see. Saturn may hold secrets stranger than storms. Its core, if it exists as modeled, is thought to be a mix of rock and ice surrounded by metallic hydrogen. But between that core and the outer layers, something unusual may be happening. Scientists believe that helium, the second lightest element in the universe, may be separating from hydrogen and sinking inward, forming droplets like rain. Helium rain. It falls through the dense fluid layers of Saturn, generating additional heat as it descends. A slow, invisible storm that has been going on for billions of years. This process helps explain why Saturn shines with its own energy, glowing gently in infrared. Saturn rotates quickly, completing a full turn in just over 10 hours, and this rapid spin flattens it at the poles and bulges it at the equator. Its shape is oblate, not quite round, as if the planet itself is being pulled toward motion. Winds whip around it at over 1,800 kilometers per hour, forming bands of color and storms that churn beneath the surface. But unlike Jupiter's vivid, multicolored belts, Saturn's atmosphere is muted. Soft yellows and grays, sometimes tinged with blue, create a more delicate aesthetic. It is a world less defined by contrast and more by layers, one blending into the next, like smoke or silk. And yet, for all its softness, Saturn exerts incredible influence. Its gravity shapes the paths of dozens of moons, from tiny pebble-like rocks to massive Titan, which holds a thick atmosphere and rivers of liquid methane. Saturn is a world of systems, of relationships, moons that carve gaps in the rings, moons that share orbits, moons that trade energy in silent tidal exchanges. Every orbit is a negotiation, every collision a reshaping. The planet is a conductor, and everything around it moves to its rhythm. To see Saturn through a telescope is to look at something impossible made real. Its rings hang in space so perfectly aligned, so luminous, that they seem more artifact than accident. But they are not permanent, and neither is our chance to witness them. The planet itself will remain, long after the rings fade, long after the probes fall silent, long after our attention turns elsewhere. But for now, Saturn stands as a reminder that even in the cold outer reaches of the solar system, there can be elegance, not chaos, not ruin, but balance, suspended in the void. A planet that would float in an ocean, a storm shaped like geometry, a core that rains helium, a halo that may vanish, and yet it endures, spinning, glowing, whispering the secrets of gas and gravity to anyone patient enough to listen. Far out beyond Saturn's golden rings, shrouded in a thick orange haze, there is a moon that feels eerily familiar, and yet is nothing like home. Titan is a place of echoes. It is Earth-like, yes, but only in structure, never in substance. It has rivers, lakes, clouds, and even rain, but none of it is made of water. On Titan, liquid methane flows across the surface, carving channels, pooling in basins, shaping deltas with a chemistry that would freeze your breath solid. It's a world that has never known sunlight as we do, and yet it carries the signature of wind and time, like a memory of Earth seen through a warped mirror. The first thing that sets Titan apart is its atmosphere. It's the only moon in the solar system with one thick enough to walk through and feel. It's even denser than Earth's, composed mostly of nitrogen with a smattering of methane and complex hydrocarbons. Light struggles to pierce it. From above, Titan looks like a smooth amber orb, its surface completely hidden beneath clouds and haze. But beneath that haze lies an alien landscape, mapped with radar and glimpsed by the Huygens probe when it parachuted down in 2005, becoming the first human-made object to touch Titan's skin. What Huygens found was astonishing. There were valleys and pebbles, carved terrain, and signs of past flows, evidence not of fire or lava, but of erosion by something liquid. And that liquid wasn't water. It couldn't be. The surface temperature hovers around -290 degrees Fahrenheit, far too cold for water to exist in liquid form. Instead, methane and ethane take its place, condensing from the atmosphere, falling as rain, collecting into rivers and lakes. Titan is the only other world in the solar system where stable liquids sit on the surface. But here, the lakes aren't blue. They're black, mirror-smooth pools of hydrocarbons, glinting under the weak sunlight filtered through 100 kilometers of haze. The landscape looks hauntingly familiar. Dunes stretch across vast plains, shaped by winds that blow through the thick, sluggish air. Riverbeds, wind, and branch, feeding into lakes with shorelines that change over time. There are seasons here, driven by Saturn's orbit around the Sun, though each season lasts over 7 Earth years. Rain falls not in gentle mist, but in slow, heavy drops of methane, splattering into the alien soil with a chemistry that would poison anything terrestrial. And yet the patterns, erosion, sediment, deltas feel like something you'd see flying over Earth's deserts or Arctic plains. It's nature, rewritten in another language. Beneath the frozen crust, deeper than the lakes and dunes, there may be something even more remarkable. An ocean of liquid water, buried under ice, warmed by the same tidal forces that knead Europa and Ganymede. It's strange to think of a hidden sea beneath a surface so violently cold. But models suggest this is likely an interior layer, perhaps mixed with ammonia, insulated from the void. And where there's liquid water, especially when mixed with organic molecules like those in Titan's atmosphere, the question of life begins to stir. Life on Titan, if it exists, would not resemble anything we know. It wouldn't breathe oxygen. It wouldn't swim through water. It would metabolize, if at all, in a chemistry we've only begun to imagine. Some researchers have theorized about methane-based life forms, organisms that use hydrocarbons the way our biology uses water. It's speculative, almost science fiction. And yet, Titan remains one of the most compelling candidates for life beyond Earth. Not because it mimics Earth's biology, but because it shows that life might not need to. The smell, if you could stand on Titan and somehow take in a breath, would be unforgettable. You'd never live to describe it, but it would be something like gasoline and oranges. The hydrocarbons that drift through the air, ethane, propane, acetylene, combine with nitrogen compounds to create a scent both sharp and oddly sweet. The haze that gives Titan its color is made of tholins, complex organic molecules formed by sunlight breaking apart methane. These tholins fall like snow, coating the ground in a reddish-brown dust. On Earth, tholins don't occur naturally, but they might be essential ingredients in the early steps toward life. Titan challenges our assumptions. It shows us that the ingredients of Earth-like landscapes, rivers, rain, erosion, don't require Earth-like materials. That the architecture of nature can be rebuilt with completely alien tools. It's a place where rocks are ice and sand is made of frozen organics, where mountains rise from frozen crusts and fog creeps over methane lakes. It's a reminder that Earth is not the only artist in the solar system. Other worlds paint, too, with different colors under different skies. Someday, we may go back. Proposals for future missions dream of floating landers, sailboats on methane seas, or even flying drones that can skim through the thick atmosphere like birds. The gravity is low, and the air is dense conditions that would allow flight with ease. A drone on Titan could travel for hours, mapping terrain, tasting the air, maybe even dipping into the lakes to sample the chemistry. One such mission, Dragonfly, is already under development, set to launch in the coming years. If it succeeds, it will take us closer than ever to understanding this alien Earth. Until then, Titan waits in silence, wrapped in haze, lit dimly by a sun that is little more than a bright star in its sky. Its lakes do not ripple with wind, but lie still, unbroken. Its dunes do not hum with life, but shift grain by grain, shaped by invisible hands. And yet everything about it speaks, not in words, but in patterns, in echoes, in the suggestion that the universe is not bound to a single formula, not limited to our imagination. Titan is not just a moon. It's a world where chemistry becomes weather, where liquids shape continents, and where the scent of gasoline hangs in the air beneath an orange sky. A place where the story of Earth is rewritten, not erased, not repeated, but transformed. Enceladus is small enough to fit inside the state of Arizona, but what it lacks in size, it makes up for in wonder. Orbiting deep within Saturn's gravity-warped domain, this icy moon drifts through the cold darkness like a cracked pearl, brilliant, smooth, and hiding something warm inside. At first glance, Enceladus looks like a snowball, white, bright, and almost featureless. But hidden beneath that frozen shell lies a secret that has captivated scientists and dreamers alike. An ocean, sealed beneath kilometers of ice, and geysers that erupt from it, spraying water into space. These plumes burst out from long, dark fissures. Near the South Pole features scientists call tiger stripes. They stretch across the surface like claw marks, carved by tides that flex the moon's crust as it orbits Saturn. The tidal forces are relentless, squeezing and stretching Enceladus over and over, warming its core just enough to melt ice into liquid. That liquid finds its way up, through the cracks, and into space, forming jets that shoot hundreds of kilometers high, casting shimmering trails behind the moon like icy breath in the vacuum. When the Cassini spacecraft passed through these plumes, it didn't just photograph them, It tasted them. Instruments on board detected not just water vapor, but salt, silica, and complex organic molecules. These weren't hints of life, but they were ingredients, pieces of a recipe that, under the right conditions, might yield something more. And those conditions, water, warmth, chemistry, are all present on Enceladus. Not on the surface, where temperatures plunge to minus 330 degrees Fahrenheit, but in the ocean, hidden below. An ocean with pressure, minerals, and a heat source. The water beneath Enceladus's shell isn't spread evenly. It pools most deeply beneath the southern hemisphere, the same region where the geysers erupt. Scientists believe there may be hydrothermal vents on the seafloor, like the ones found in Earth's deep oceans. On our planet, such vents teem with life thriving without sunlight, fed by chemical energy from within the Earth. If similar vents exist on Enceladus, they may offer a habitat not just for organic molecules, but for organisms, microbes, simple cells, life, small but significant, surviving in the black depths of a moon. And this water doesn't stay hidden. The geysers throw it outward in such volume that it creates Saturn's E-ring, a vast, ghostly halo that encircles the planet, made almost entirely of particles from Enceladus. The moon is literally shaping its parent planet's system, leaving a mark visible across hundreds of thousands of kilometers. It's one of the few known examples of a moon actively contributing to a planet's ring structure. The plumes are not a one-time event. They're continuous, persistent, a sign that the internal ocean is not sealed away, but connected to the vacuum of space by pathways of ice and pressure. Because of its reflective surface, Enceladus is one of the brightest objects in the solar system. It reflects almost all of the sunlight that hits it, glowing like a beacon against Saturn's dark sky. And yet, it is this very brightness that conceals its secrets. Only by flying close by, getting dust on the instruments and frost on the sensors, were we able to see what was truly there. Cassini did not land, but it came close enough to pass through the icy spray. Close enough to raise the possibility that, with the right tools, we could return not just to study, but to sample, to capture and analyze and search for traces of something that breathes. Enceladus is strange in its balance. It is ancient and active, frozen and flowing, a world that seems asleep until you look at it the right way. It doesn't roar with storms like Jupiter, or glow with volcanoes like Io. It doesn't dominate the sky with rings or atmosphere. It whispers, but that whisper carries the weight of enormous possibility. The idea that something so small, so easily overlooked, might harbor life is a powerful one. It redefines where we search and what we expect. Enceladus shows us that you don't need Earth-like temperatures or open oceans to support the conditions for biology. You just need energy, water, and time. And this moon has had all three for billions of years, locked beneath a crust of shifting ice, warmed by the gravity of a distant planet, and stirred by forces we can measure but not yet fully explain. We've seen the water. We've detected the chemistry. We know the ocean is there. What we haven't found yet is life, but the ingredients are in place. And unlike many other candidates for habitability, Enceladus doesn't hide its ocean behind miles of rock or sealed crust. It flings it into the void, over and over again, inviting us to catch it. To stand on its surface would be to hear nothing. There is no sound, no air to carry it. But in the silence, the geysers would rise and fall, again and again, like frozen fireworks. Light from Saturn might glint through the haze, casting long shadows across the snow. The ground beneath your feet would be smooth, in some places, cracked in others, shaped by impacts and pressure and time. And somewhere far below, in a sea without light, something might be moving. Enceladus reminds us that the universe is not simple, that life may not need sunlight, or warmth, or continents. It may need only a chance, a crack, A vent, a little heat in a dark place, and that sometimes the most promising worlds are not the loudest ones, but the quiet moons that cast snow into space, again and again, like a signal in the dark. In the cold reaches of the solar system, where sunlight thins to a pale thread and planets drift like frozen thoughts, Uranus rolls along its orbit like a world that once fell and never stood up again. While every other planet spins more or less upright, Uranus is tipped almost completely sideways, its axis tilted at a staggering 98 degrees. It doesn't spin like a top, but like a ball rolling on its side. Its poles, not its equator, take turns facing the sun, and each season lasts for decades. A strange planet with strange behavior, cloaked in a soft blue light that hides more than it reveals. The color is due to methane in its atmosphere, an icy gas that absorbs red light and scatters blue. But beneath that serene hue lies the coldest planetary atmosphere in the solar system, dipping below -370 degrees Fahrenheit. It's a quiet kind of cold, not the howling void of a gas giant's storms, but a stillness so deep it becomes eerie. Uranus doesn't flash with violence the way Jupiter does. Its winds are fast, yes, and storms have been detected, but they do not rage across its surface in easily visible belts. Instead, its calm is misleading. It's not a lack of activity, it's a difference in mood. The sideways tilt has consequences beyond aesthetics. During its 84-year journey around the sun, each pole spends over 20 years in continuous sunlight, followed by 20 years of darkness. Imagine a world where the sun rises once in a human lifetime, then sets, decades later. The seasonal changes are not just long, but profound, likely driving deep atmospheric shifts and movements we still struggle to fully observe. Summer on Uranus means one pole is bathed in light, while the rest of the planet shivers. Then, slowly, the light crawls around, and winter descends for another generation. Why Uranus is tilted this way is still debated. The most likely explanation is impact some massive object, perhaps the size of Earth, collided with it in the early days of the solar system, knocking it sideways. But the memory of that event is buried deep, encoded in the motion of its moons, the warp of its magnetic field, and the unusual rotation of its interior. It is as if Uranus absorbed the blow without breaking, carrying the scar in its stance. Its ring system is faint but real, a delicate set of narrow bands, discovered not by sight but by shadow. When a star passed behind Uranus in 1977, astronomers noticed flickers of starlight vanishing and reappearing, as if something was briefly blocking the view. That something was rings thin, dark, composed of dust and ice, orbiting close to the planet's equator. Unlike Saturn's majestic display or even Jupiter's wispy arcs, Uranus's rings are subtle, requiring precision to detect. They are there, but they do not announce themselves. The planet's magnetic field adds another layer of strangeness. Unlike Earth's relatively aligned field, Uranus's magnetic field is wildly tilted and offset from its center. It emerges not near the poles but near the equator, tilted by 59 degrees from the planet's rotation axis. The result is a magnetic environment that twists and flips as the planet rotates, creating a lopsided, lurching magnetosphere that behaves unpredictably. Particles are trapped and thrown in uneven arcs, and auroras flicker in patterns that make little sense compared to the tidy displays on Earth or Jupiter. Despite its distance and obscurity, Uranus has moons, 27 that we know of. They orbit in the planet's equatorial plane, which means they too roll sideways around the sun, like dancers in a tilted ballet. Many are named after characters from Shakespeare and Alexander Pope, a poetic choice for companions of a planet so dreamlike. Miranda, one of the smallest, shows a fractured surface of cliffs and canyons that hint at a violent past. The moons, like the planet they orbit, carry stories written in ice and shadow. Uranus is often treated as an afterthought in planetary exploration. Only one spacecraft has ever flown past it. Voyager 2 in 1986. The images it returned were pale and smooth, and for years the planet was labeled dull. But we now know that Voyager's instruments simply caught Uranus in an unusually calm phase. Newer telescopes have revealed more dynamic weather, deeper layers, and signs of activity that were once missed. The planet is not quiet. We were simply not listening closely enough. To understand Uranus is to embrace contrast. It is a gas giant with icy qualities, a calm world that hides ferocity, a planet that spins sideways but moves forward all the same. Its seasons stretch longer than childhood. Its storms are whispered, its rings are shadows, and its magnetic field dances out of step, as though it refuses to be tamed by symmetry. What makes Uranus captivating is not drama, but dissonance. It is the feeling of watching something that should be simple behave in ways that defy expectation. A sphere tipped onto its side, glowing faintly blue, holding its moons close and its secrets closer. It does not demand attention, but quietly rewrites the rules. It teaches us that strangeness can be subtle, and that even in the coldest corners of the solar system, there is beauty, not loud or bright, but deep, offbeat, and hauntingly graceful. Neptune drifts at the far edge of our planetary family, cloaked in deep indigo and mystery. It is a world sculpted by distance and darkness, where the sun is little more than a bright star, and the days pass in silence, broken only by storms the size of Earth. Though it lies nearly 3 billion miles from the warmth of the sun, Neptune is anything but still. Its atmosphere seethes with violence, home to the fastest winds in the solar system, some reaching over 1,300 miles per hour. Winds so swift they would shred the clouds from any earthly sky. The outermost giant, Neptune is cold in temperature but fierce in temperament, a contradiction wrapped in cobalt. Those winds churn the methane-laced clouds into wild formations, building storms that come and go like passing moods. In 1989, Voyager 2 flew past and captured images of a massive vortex, the Great Dark Spot swirling near the equator, echoing Jupiter's Great Red Spot but darker, faster, more ephemeral. Unlike Jupiter's centuries-old storm, Neptune's vanished not long after it was seen. Others have formed and faded since then, appearing in different locations, refusing to stay for long. On Neptune, even storms do not last forever. They are not monuments, they are moments. Yet for all its distance and thin sunlight, Neptune glows with energy. It radiates more than twice the heat it receives from the sun, an internal warmth that remains poorly understood. Some scientists suspect the source lies deep within, perhaps the slow settling of materials in the core, or lingering heat from the planet's violent birth. Whatever the cause, Neptune carries its own fire, buried beneath layers of hydrogen, helium, and icy gases. It doesn't need sunlight to shine. Its color is deeper than that of Uranus, despite a similar atmospheric composition. The exact reason is still a mystery, likely due to unknown trace elements or subtle differences in cloud structure. But the result is a planet so vividly blue it feels painted by imagination, a place where storms blur into canvas-like streaks, and the boundary between cloud and atmosphere seems to ripple like silk. Orbiting this blue giant is Triton, a moon unlike any other. It spins in the wrong direction, a retrograde orbit that defies the motion of its parent. All other major moons in the solar system orbit in the same direction their planet rotates, but Triton moves backward, a silent rebel. This alone hints that it did not form alongside Neptune, but was captured perhaps once a dwarf planet wandering the Kuiper Belt, pulled in by Neptune's gravity and transformed into a moon. But Triton's strangeness doesn't end there. Its surface is icy and smooth, marked by frozen plains, geysers of nitrogen, and few impact craters. It is active, geologically speaking, despite its distance from the sun, and deep below its frozen crust, scientists suspect there may be an ocean of liquid water kept warm not by sunlight, but by tidal flexing and radioactive decay. A potential ocean beneath a world that should be too far, too cold, too still. Even Neptune's atmosphere hides wonders that border on the surreal. At extreme pressures deep below the clouds, carbon atoms may be squeezed into something new diamonds. The conditions are so intense that scientists believe it may literally rain diamonds inside the planet. Carbon drifting down as soot, crushed into crystal, falling through layers of ice and gas in silent, sparkling showers. A storm of gemstones in a place no human has ever seen. To imagine this is to feel the weight of Neptune's alien beauty, a place where the winds never stop and rain is made of jewels, where storms bloom and vanish, and a captured moon spins the wrong way, whispering secrets from a time before planets had names. Neptune is not a world of gentle rhythms or familiar patterns. It is a world of extremes, cold, fast, and fierce, and yet it carries a certain stillness too, a quiet that comes with distance, the kind of quiet found only in the outer dark, where sunlight barely stirs and time seems to stretch. Neptune orbits far beyond Saturn, and Jupiter, beyond the asteroid belt, beyond the warmth and chaos of the inner solar system. It takes 165 Earth years to complete a single orbit. Since its discovery in 1846, it has yet to return to the same place in the sky. A full Neptunian year has not passed since we first gave it a name. It moves slowly, but everything within it moves fast. There's a lesson in that contrast, a reminder that speed and stillness can coexist, that distance doesn't mean silence, and that some of the most dynamic worlds lie hidden beyond the veil. We've only visited Neptune once. Voyager 2 offered us a brief, tantalizing glimpse before continuing on its path out of the solar system. No other spacecraft has returned. No orbiters, no landers. It remains, for now, a mystery suspended in blue. We see it through telescopes, chasing its movements, tracking its storms, watching its moon. But it waits, quietly, for a closer look, for a second chance. Neptune is the ocean planet not made of water. It is the wind king, the diamond realm, the keeper of storms and backward moons. It reminds us that the edge of the solar system is not the end of wonder. It is only the beginning of what we have yet to understand. Pluto is not the coldest, nor the largest, nor even officially a planet by modern definitions, but it has become, in many ways, the soul of the outer solar system. Small enough to be dismissed, distant enough to be forgotten, yet filled with features so strange and stirring that when the New Horizons spacecraft flew past in 2015, the world paused to look. And what it saw wasn't just a frozen rock. It was a place with heart, literally. A vast, bright plane in the shape of a lopsided heart, etched across the face of this lonely world like a message to anyone watching from afar. That heart-shaped region is called Sputnik Planitia, a frozen basin of nitrogen ice that stretches wider than Texas. It rests in the western lobe of the heart and is smooth, young, and alive with motion. Unlike ancient cratered highlands, this plain is nearly free of impact scars, suggesting that it is being resurfaced from below, possibly by slow-moving convection cells in the thick layer of ice, or perhaps by cryovolcanism that breathes new material up from Pluto's deep interior. At its edge, the ice curves into ridges and troughs, shaped not just by time, but by the thin pull of Pluto's gravity and the quiet insistence of internal heat. To the south of Sputnik, Planitia rise mountains of ice taller than the Rockies. These are not made of rock, but of frozen water, so cold and hard in Pluto's frigid environment that they behave like stone. Towering peaks like Tenzing Montes and Hillary Montes stretch into the sky, their jagged ridges casting long shadows over the plains. These mountains are vast, ancient, and still standing, even in a world where warmth is measured in whispers and sunlight is only a faint glimmer. Pluto has an atmosphere too, thin and tenuous, composed mainly of nitrogen with hints of methane and carbon monoxide. It clings delicately to the surface, expanding when Pluto is closer to the Sun and freezing out as it retreats to the far edge of its elliptical orbit. This ephemeral envelope creates hazes and layered skies, sometimes forming clouds that drift in the cold, clear air. When backlit by the Sun, Pluto's atmosphere glows in soft blues, reminding us that even a dwarf planet can carry the breath of something vast. Orbiting Pluto are 5 known moons, each with its own rhythm, but none more captivating than Charon. Charon is not just a moon. It is nearly half the size of Pluto itself, making the pair more like a binary system than a planet and satellite. They orbit a shared center of gravity that lies outside of Pluto's surface, locked in a gravitational dance where the same face of each always looks toward the other. Charon's surface is scarred and split, with a dark red cap at one pole and a canyon system so vast it dwarfs the Grand Canyon many times over. Together, Pluto and Charon move through the Kuiper Belt like twin shadows, bound by distance, divided by space, but forever linked. Pluto's orbit is eccentric, tilted, and distant, sometimes bringing it closer to the Sun than Neptune. And yet, the two never collide. They are locked in a 3-to-2 resonance, meaning Pluto completes 2 orbits for every 3 of Neptune's. This resonance keeps them in harmony, like celestial notes in a cosmic chord. Though their paths cross in theory, their dance is stable, orchestrated by gravity across millions of years. And still, Pluto remains a mystery. Its surface is a patchwork of dark and light regions, some as black as coal, others as bright as freshly fallen snow. The darkness is tholins, complex organic compounds formed by radiation and sunlight interacting with methane. These tholins drift and settle, coloring craters, covering ridges, and tinting the poles. They are not signs of life, but they are the kinds of molecules that life could build from, given the right spark and shelter. Before New Horizons arrived, Pluto was little more than a blur, a pixelated dot at the edge of understanding. But as it came into focus, it revealed itself not just as a destination, but as a reminder that small does not mean simple, that distant does not mean dead, that even the farthest reaches of the solar system can hold stories carved in ice and time. Pluto, in its quiet way, challenges our assumptions. It resists categories, blurs definitions, and humbles every tidy list we try to make of the cosmos. It is a place that defies expectation, not by scale or fire, but by complexity, by the subtle layering of terrains, by glaciers that creep across its surface, by a heart that rises out of cold nitrogen and faces the stars. It is not alone, not forgotten, and not silent. It turns slowly, draped in night and snow, circled by moons, and lit by a sun that barely warms it. And yet, it moves. It evolves. It holds on to an atmosphere. It reshapes its plains. It carries its history and impact scars, and its hope in the possibility that under its crust, a hidden ocean might still ripple in the dark. Pluto is not a footnote. It is a chapter, a reminder that wonder doesn't need size or category to matter. It just needs a heart. Beyond Neptune's slow path lies a region neither fully dark nor fully understood. It stretches like a whisper around the outer edge of our solar system, a band of distant, frozen worlds and ancient debris called the Kuiper Belt. Here, sunlight weakens until it barely brushes the surface of ice and rock. Here, time seems to slow. This is not a place of glowing planets or blazing storms. It is a graveyard of ghosts, not of what died, but of what never became. A relic field of the solar system's earliest days, filled with pieces that never formed into planets, left behind like forgotten pages from the first draft of a story. The Kuiper Belt is cold, but not empty. It is crowded with fragments. Billions of icy bodies drift here small, silent, and scattered. Some are no larger than mountains, while others, like Eris, Haumea, and Makemake, rival Pluto in size. These are the dwarf planets of the belt, drifting slowly through a region so vast that they can go centuries without encountering anything else. Yet for all its desolation, this place holds secrets that may reshape how we understand the beginning of everything. These frozen objects are time capsules, unchanged for over 4 billion years. While planets melted and churned and grew complicated, these fragments remained untouched. Preserved in the deep freeze of space, their surfaces are etched with the faint scars of ancient collisions, their interiors potentially hiding mixtures of rock, ice, and organic compounds. They are the raw ingredients of worlds that might have been. To touch them would be to hold a piece of the past in your hands, the kind that existed before Earth had oceans or air. Some of these Kuiper Belt objects are binaries, pairs that orbit each other in a slow, looping dance. Unlike moons tethered to planets, these pairs are more like companions, drifting together through the dark, locked not by gravity alone, but by shared origins. Their balance is delicate. Two icy spheres bound by distance, neither large enough to dominate the other. It's a kind of harmony that feels rare and quiet, like music played in a language we haven't learned to hear. The belt itself begins around 30 astronomical units from the Sun just past Neptune, and may stretch out to more than 50 AU, where it begins to blur into the even more mysterious scattered disk, and eventually, the edge of the Heliosphere. And yet, there is no clean boundary, no wall, no curtain, just a fading of gravitational order as our solar system begins to dissolve into the interstellar medium. The Kuiper Belt may simply vanish into that void, particle by particle, world by world, until its last fragments are indistinguishable from the chaos between stars. We've mapped only a fraction of it. There could be thousands more dwarf planets, tumbling slowly in paths we've never traced, waiting in orbits too distant or dim for our telescopes to catch. Even Pluto, once considered the solar system's final planet, was just the first clue that something larger was out there. New Horizons confirmed that suspicion in 2015 when it sailed past Pluto and continued into the Kuiper Belt, visiting Eris, a contact binary shaped like a snowman, with two lobes fused gently together, untouched for eons. Its smooth surface and soft contours hinted at a formation so slow, so careful, that it rewrote how scientists think small worlds might emerge from dust. But it also underscored something else, that the Kuiper Belt is not dead. It is quiet, yes, and remote, but it moves, it shifts. Some of its members are nudged by Neptune's gravity, slowly, migrating over millions of years. Some are pulled into the inner solar system, transformed into short-period comets, trailing icy tails as they pass the sun and begin to sublimate. These glowing visitors, admired from Earth with awe and curiosity, are messengers from the belt, bearing news from a realm we barely understand. If you stood on a large Kuiper Belt object, the sky would be black, but it wouldn't be empty. The sun would be a sharp point, bright enough to cast shadows but small enough to cover with a fingertip. Around you, space would stretch in every direction, cold, quiet, immense. Nothing would move quickly, nothing would glow. But if you waited long enough, you might see the drift of another body on the distant horizon, slowly crossing the sky like a forgotten thought. The Kuiper Belt may hold the key to planetary formation, or the ingredients for life, locked in frozen methane and carbon chains. Or perhaps it holds nothing at all but the weight of time and an archive not meant to be read, only remembered. It challenges us with its silence, invites us to look deeper, beyond the borders we thought we knew. And while it may seem like the end of the solar system, it isn't. Beyond the Kuiper Belt lies the Oort cloud, and beyond that, the void between stars. The belt is not a wall, it is a threshold, a liminal place between what we've seen and what we've yet to find. A glittering graveyard, yes, but also a museum, a map, and maybe one day, a path. Out here, the solar system exhales. It slows. It remembers. And for those who listen, it still has stories left to tell. Far beyond the planets and moons, past the icy trails of comets and the scattered whispers of the Kuiper Belt, there is believed to be a boundary so distant it blurs the line between our solar system and interstellar space. It is not a place we have seen, or mapped, or touched. It is more a shadow of prediction, a silhouette drawn by gravity and mathematics. But it may be the most vast and ancient structure tied to our sun, a spherical shell of frozen debris known as the Oort cloud, a ghostly halo of icy remnants left over from the dawn of time, suspended on the edge of everything. The Oort cloud has never been directly observed. No telescope has spotted it. No probe has flown through it. And yet, its presence is echoed in the comets that occasionally sweep into the inner solar system. A long-period wanderers with orbits so wide and slow, they seem to fall in from the stars themselves. Their paths are too strange, too vast to originate from the planets or the Kuiper Belt. They come from further out, from the deep freeze of a shell that could extend up to a full light year from the sun. If the solar system were the size of a city, the planets would be crowded in the downtown core, but the Oort cloud would be like a lonely ring of suburbs 100 miles away, dark, quiet, and almost forgotten. Within this invisible cloud may be trillions of icy bodies. Most are small, less than a few kilometers across, made of rock, dust, and frozen gases like water, ammonia, and methane. They drift slowly, caught in the most fragile grasp of the sun's gravity, so distant that a light signal from Earth would take months to reach them. They are bound to us, but only just. A strong enough nudge from a passing star or a ripple in the galactic tide could send one tumbling inward, beginning a journey that takes millions of years and ends with a glowing arc across Earth's sky. These objects are ancient. They formed when the solar system was young, during the chaotic swirl of planet formation. Many began life much closer to the sun, but were flung outward by gravitational slingshots, cast off by the giant planets during their migration through the early solar disk. Some were ejected entirely, sent into the void to wander the galaxy. But others lingered, slowed by the sun's last faint pull, settling into distant, elliptical orbits that eventually formed the great icy shell. The Oort cloud isn't flat like the planetary disk or even the Kuiper Belt. It's spherical, a vast, diffuse halo surrounding the solar system in every direction, a fragile bubble of frozen potential, with an inner edge perhaps around 2,000 astronomical units from the sun, and an outer boundary that may reach 100,000 AU, a quarter of the distance to the nearest star. The numbers are so large they feel abstract, but they mean that our solar system, if seen from afar, might not look like a tidy disk at all. It might shimmer faintly with the invisible breath of these ancient fragments, wrapped in a sphere of ghosts. And yet, despite its size, the Oort cloud remains elusive, because the objects within it are so far and so small, they reflect almost no sunlight. They don't glow, they don't radiate, and unless one is disturbed, they remain hidden. Our best evidence for the cloud comes from the comets that appear, unexpectedly, tracing long, slow arcs through the sky. Some take tens of thousands of years to complete a single orbit. Others may pass once and never return. Each is a messenger from the edge, a flicker from a realm we've never truly seen. Comets from the Oort cloud are different from those that come from the Kuiper Belt. Their orbits are more eccentric, more tilted, more unpredictable. They don't just skim the outskirts, they plunge deep, swinging close to the sun before retreating again into the dark. Their appearances are rare but dramatic. In ancient times, their sudden arrivals inspired awe, fear, and prophecy. Even today, they remind us that the solar system is not a closed loop, but a living system, one that breathes icy strangers from its deepest memory. The Oort cloud also marks a kind of boundary not just of distance, but of control. It represents the outermost limits of the sun's influence, the edge of where its gravity can still hold sway against the pull of the galaxy. Beyond this shell lies true interstellar space, where other stars hold their own clouds, and the void stretches uninterrupted between systems. It is here that the sun's dominance fades, not with a wall, but with a slow, graceful surrender. The Oort cloud is the solar system's final whisper, a fading note at the edge of the song. One day, a spacecraft may reach it. Voyager 1, Voyager 2, New Horizons. They are all headed outward, slipping toward that distant threshold. But it will take them thousands of years to cross it. By the time they arrive, if they endure that long, humanity may have changed entirely or disappeared. Still, they travel. Still, they seek. The Oort cloud is a paradox vast, filled with countless objects, and yet nearly invisible. It is made of leftovers and yet could outlive the planets. It is distant beyond imagination, but quietly connected to us through every long-period comet that lights the night. We can't see it, but it surrounds us. And in that unseen stillness, wrapped in darkness, lies a story that began with the birth of the sun and may echo until long after the last planet cools. In the grand clockwork of the solar system, not everything fits neatly into orbits and categories. Between the planets and their moons, beyond the belts and clouds, and weaving through every patch of open space, there is a drifting population of strays, leftover particles, shattered remnants, icy wanderers, and fire-streaked messengers. These are the cosmic drifters. They are comets and meteoroids, specks and boulders, dust and ice and ancient memory, colliding and falling and waiting. Their stories are brief but bright. Some blaze through our skies in seconds, others take centuries to return. They are small, but they carry weight, the weight of history, the weight of change. Comets are the ghosts of the deep solar system, icy bodies formed in its coldest corners. Most come from the Kuiper Belt, or the even farther, Oort cloud, and they spend most of their lives in frozen silence. But when a comet ventures inward, drawn close by the pull of the sun, it begins to awaken. Ice turns to vapor, dust breaks free, and a tail forms a luminous plume that can stretch millions of kilometers behind it, pointing not where the comet is going, but away from the solar wind. This tail is not a single thing, but a separation. Dust drifting slowly, light scattered in broad arcs, gas swept into a narrower stream, glowing with ionized color. It is a sign of motion, of transformation. Comet tails are ephemeral, but they leave traces. As Earth moves through space, it often crosses these invisible trails, remnants of old comet paths scattered like grains across the sky. And when it does, those tiny pieces, sometimes no larger than a grain of sand, burn in the upper atmosphere, flaring briefly as meteors. Meteor showers like the Perseids or Leonids are born this way, regular encounters with the debris, fields of long-gone comets. What we see is not the fall of something new, but the brief combustion of something ancient, catching fire one final time before vanishing. And not all comets are consistent. Their orbits shift with time. The push and pull of gravity from planets, from the sun, even from passing stars can alter their paths. Some comets return predictably, like Halley's Comet, looping back every 76 years. Others take millennia, their return so slow that civilizations rise and fall before they appear again. And some never return at all, captured by the sun or flung outward into the darkness, lost forever. Their trails, however, remain a kind of scar across space, invisible until the Earth moves through it again. But comets may carry more than just dust. Within their icy cores lie frozen gases and complex organic molecules in the building blocks of life. It is possible that some of Earth's earliest ingredients arrived this way, delivered by impacts when the planet was young and still forming its oceans. Hydrogen cyanide, formaldehyde, Even amino acids have been detected in comet samples. What once seemed lifeless and distant may have played a role in life's beginning, a frozen messenger, becoming a catalyst. Yet for all their brilliance, most meteoroids are minuscule. They float unnoticed until Earth's gravity pulls them in and friction lights them up. When they burn, they can seem vast streaks of light racing across the night, sometimes green or orange or gold. But the object itself is often no larger than a pebble. Only the largest survive the journey through atmosphere, becoming meteorites when they strike the ground. These fragments are studied, treasured, and sometimes feared. Because while most meteoroids are harmless, a few have not been. In 1908, over a remote forest in Siberia, something exploded in the sky. The blast flattened thousands of square kilometers of trees, creating no crater, but a shockwave so strong it was felt around the world. The event is known as the Tunguska incident, and it was likely caused by a small asteroid or comet fragment, no more than 60 meters across. It never touched the ground. The explosion occurred mid-air. Had it happened over a city, it would have erased it, and while it was rare, it was not unique. Events of that scale occur more often than we'd like to think, perhaps every few centuries. Most fall into oceans or uninhabited lands, but the risk remains. Even smaller events happen constantly. Earth is bombarded by over 100 tons of meteoroid material each day, mostly dust and tiny fragments that go unnoticed. Some settle in polar ice or the deep sea. Some fall onto rooftops. Most are never found. But they are always arriving, reminders that Earth does not move alone. We travel through a minefield, and our atmosphere is both a shield and a stage, catching, burning, erasing. These drifters don't fit into grand orbits or planetary charts. They are not defined by size or shape. A single grain can paint a streak across the sky. A frozen core the size of a city block can ignite wonder across the world. And while they are not planets or moons, they connect us to the larger whole. The debris tells the story of everything else, of collisions that didn't form planets, of objects that were cast away, of events that shaped landscapes in fire and dust. Even now, some meteorites carry trapped gas bubbles older than the Earth. Some contain isotopes that tell of explosions from other stars. Others have magnetic imprints from their birth in solar disks. They are time travelers, crossing distances not in years, but in deep cosmic patience. And they remind us that not everything bright in the sky is big. Sometimes, it's the smallest things that leave the deepest impressions. In the quiet dark of space, where time unspools in silence and light, travels like a whisper across billions of miles, the solar system is never truly still. Beneath the measured paths of planets and the slow drift of moons, there is motion and tension, flickers and surges, oddities that ripple through the calm. It is a place of rules, gravity, inertia, thermodynamics, but also of strange exceptions. Phenomena that bend expectation. Moments that reveal that the universe is never as predictable as it first appears. From Earth, we watch for planetary alignments with a mix of curiosity and superstition. Occasionally, several planets gather in the sky, lined up in our view, a celestial choreography that feels too precise to be chance. Yet these alignments are illusions of perspective, brief arrangements in our shared orbital waltz. They do not summon earthquakes or open portals or tilt the Earth's axis, but they are beautiful. And for ancient civilizations, they must have seemed like omens. Today, they remind us that even randomness can form patterns, if only for a moment. Not all strange sights in the solar system are tricks of perspective. Some are real and unexpected, like moons that wear cloaks of atmosphere. Titan, Saturn's largest moon, is wrapped in a dense orange haze, thicker than Earth's air, where methane rains fall into lakes of hydrocarbons. Triton, Neptune's captured moon, exhales geysers from beneath its icy shell, sending wisps into its fragile atmosphere. Even the tiny moon Enceladus breathes vapor into space, building a kind of exosphere with every eruption from its south pole. These are not dead rocks. They are dynamic, reactive, and occasionally stormy. Space, though silent, has weather of its own. And sometimes, the sun is the source of the storm. Its surface seethes with magnetic activity, flinging out charged particles and solar wind in great arcs and bursts. When these waves strike a planet, they can disturb magnetospheres, spark geomagnetic storms, and trigger aurorae. On Earth, this means shimmering curtains of green and red that ripple across polar skies, the aurora borealis and aurora australis. But Earth is not alone in this spectacle. Jupiter's poles flash with ultraviolet aurorae, larger than our planet, fed not just by the solar wind, but also by volcanic gases from its moon Io. Saturn pulses with ghostly ovals of light, glowing in infrared silence. Even Uranus and Neptune, far from the sun's direct touch, display faint auroral rings, distorted by their tilted magnetic fields. Sometimes these solar storms do more than dazzle. When Earth is in the path of a strong coronal mass ejection, a massive burst of solar plasma, the result can be more than just aurorae. Our satellites can be fried. Communication signals can be disrupted. Entire power grids, like the one in Quebec in 1989, can be knocked offline in seconds. We call it space weather, as if it were something gentle, something to be forecasted. But in reality, it's a force of nature, capable of turning night to light and technology to silence. Yet humanity has learned to use the quirks of this environment as well. One of the most remarkable tools in our exploration of the solar system is the gravity assist. By carefully navigating a spacecraft near a planet, we can steal a little of its momentum, not enough to alter the planet's path, but enough to slingshot our craft forward at incredible speeds. It's like borrowing the arm of a giant to throw a stone. The Voyagers used Jupiter and Saturn to leap toward interstellar space. Cassini danced between Venus and Earth before slipping into Saturn's embrace. The Parker Solar Probe, in its quest to kiss the Sun, circles Venus again and again, tightening its orbit with each pass. These are not brute force journeys. They are dances of precision, timing, and an understanding of gravity so deep it becomes art. All of this, the strange orbits, the electric skies, the invisible storms, paints a portrait of a solar system that is more alive, more responsive than we once believed. It is not a collection of still objects frozen in place. It is a system in flux. It breathes in magnetic fields and exhales radiation. It listens to the song of the sun and answers in aurorae. Its moons whisper gas into space. Its planets tilt and spin in quiet defiance. And its debris races in slanted orbits, lit briefly when caught by Earth's gaze. Some phenomena can be seen, others must be inferred. But each reminds us of how much we have yet to understand. Because even now, with our probes and telescopes and data models, we still find surprises. Magnetic fields that twist in unexpected directions. Storms that form where no clouds should be. A comet that disintegrates without warning. A signal that flickers for just 1 second longer than it should. The solar system is not finished telling its story. It's still writing chapters, sometimes in plasma, sometimes in dust. And through all the oddities, it invites us to look closer not just for answers, but for better questions. The system has never been a fixed arrangement, never a finished design. What we see today, the ordered rings of Saturn, the frozen plains of Pluto, the whirling clouds of Jupiter, is only one moment in an ongoing story, a single still frame from a film that began long before us and will continue long after we're gone. Everything is moving, everything is changing, and much of it we're only just beginning to understand. Planet migration is one of those unsettling truths that rearranges the neatness of our early education. For decades, we imagined the planets forming where they now reside, each one coalescing from the disk of gas and dust that circled the newborn sun. But the deeper we looked, the more the evidence whispered a different tale. Jupiter, the giant of giants, may not have always ruled where it does now. Early models suggest it wandered inward first, possibly reaching as close to the sun as Mars does now, before retreating outward again, its motion dragging, and scattering asteroids and reshaping the architecture of the entire solar system. Saturn, too, might have played a role in this celestial reshuffling, its gravity tugging against Jupiter's, setting off waves and eddies in the protoplanetary disk that carved pathways for other planets to follow. Uranus and Neptune may have switched places. The asteroid belt, that broken ring of space rocks between Mars and Jupiter, might be the shattered remnants of a planet that tried and failed to form, torn apart by these migrations. What looks stable to us now is really the settled echo of ancient turbulence. Even now, long after the chaos of planetary formation has subsided, change continues, sometimes so slowly we can't feel it. Moons drift, orbits wobble, rings dissolve and reform. The moon, Earth's silent companion, is inching away from us each year about as fast as our fingernails grow. It's a gentle farewell, millimeter by millimeter, but one with consequences. Millions of years from now, Earth's tides will be weaker. The day will stretch longer. The moon, now our guardian against spin and tilt, will someday be too far to hold us steady. Meanwhile, Saturn's rings, those luminous, iconic bands, are vanishing. Cassini revealed the truth. The rings are raining down, dust and ice, pulled by gravity, falling into Saturn's atmosphere like soft snow. In cosmic terms, they are young and temporary, perhaps only 100 million years old, and may vanish entirely in another few hundred million. What we see today, in their grace and elegance, is a rare sight, a fleeting phase in Saturn's long life. And the sun, at the center of it all, is quietly preparing for a transformation of its own. For now, it burns with steady fusion, turning hydrogen into helium in its core. But one day, that fuel will run low, and when it does, the balance will tip. The sun will bloat into a red giant, swelling beyond the orbit of Mercury, possibly Venus, maybe, even Earth. Its surface will cool as it expands, but its core will grow hotter, fusing helium in a final blaze of life before it collapses into a white dwarf, a ghost of its former self, glowing with leftover heat for billions of years. That future is distant, measured not in centuries but in billions of rotations. But already, we're part of that story. Humanity has left footprints on the moon, robotic trails on Mars, golden records sailing past the edge of the sun's reach. Our satellites orbit in silent paths. Our telescopes peer outward with unblinking eyes. And soon, perhaps, humans will walk on Mars, build habitats in orbit, or float among the clouds of Venus in high-altitude balloons. We are beginning to reshape our relationship with the solar system, not just as observers, but as participants. And yet, for all our growing reach, we are fragile here. The system we live in is alive in ways we often forget. A comet we never saw coming could streak past with a tail, million kilometers long. A solar flare could cripple our satellites. A slight tilt in Earth's axis, or a small change in orbit, could shift climates over millennia. The ground we stand on drifts, carried by continental plates that move with the same patience as glaciers. Our calendars adjust for leap seconds, because Earth's spin is not perfectly constant. The solar system is not a clock. It is a breathing, shifting organism. Its rhythms stretch beyond our lives, beyond the lives of nations or civilizations. Volcanoes erupt on distant moons. Magnetic fields crackle and pulse. Icy objects in the Oort cloud shift in silence, nudged by distant stars or unseen gravity. In the cold beyond Neptune, new dwarf planets await discovery, and perhaps somewhere in a hidden ocean beneath Europa's ice, something swims, We are the only species we know of that can witness this, that can map it, measure it, tell its story. We are children of stardust, born from the debris of earlier stars, assembled by gravity, shaped by time. And now, we ask questions. We send machines to answer them. We look outward not just to escape, but to understand where we came from. The solar system is not finished. Its future is not fixed. It is a living thing, vast, strange, and always changing. And we are part of it, just for a little while.